All right, so today we continue with the background on group actions. Probably, hopefully, in the end of the class, we touch upon some symplectic story again, and we definitely return to discussing symplectic geometry now combined with group actions next time. So this is a continuation of this chapter 3. Let's say group actions. Continued. Well, so here is our context. G is a Lie group, and let's say M is a manifold. And G acts on M, so sometimes that's the notation for it. So G acts on M, and this means that there is a map from G cross M to M. Here there are many possible notations. To be honest, I rarely use this complete notation, A of GM. Often I'm writing G dot M, or sometimes when it is more suitable, M to the power G. So this is all the same. So the element of the group G acting, moving the point M somewhere. So you can imagine something like this, right? So here is our point M. Here is the point MG. And so the element G moves it there. And of course, we impose a condition on that map. And the condition for the group action, just to remind you, is as follows. If we act consecutively by two group elements, right? So I'm acting here first by H and then by G. So that's the same as to act by the product in the group of G and H. Of course, we're going to see many examples of it, but now let me just introduce a little bit of a terminology. So a little bit of language, what that we are using to describe this situation. Suppose we choose a point M on the manifold, and then naturally there is something which is called the orbit of M. So these are all the points that you obtain from M by acting by different group elements, right? So here you can imagine that this is our point and this is its orbit. To the point M, we can also assign a subgroup within the group G. So these are all elements of G which have the following property. So when G acts on M, you just get the same point. So these are the group elements which don't move the point M. So this is called the stabilizer subgroup of M. So this is sitting inside G, and here I guess you probably know it because you probably seen such things in other courses. But just if you never seen it, so this is a subgroup, and if you never seen it, maybe it's a good thing to check. This is indeed a subgroup. So this GM. Now, maybe one fact that will be useful later on. There is a relation between OM and GM, and the relation is like that. So OM is isomorphic to the quotient space of G by GM. So maybe here is here is a map. So write elements of the quotient space. These are cosets, right? So for instance, G, GM, and you map it to a point G dot M in OM. So this map gives you an isomorphism between the coset space or the quotient space and or homogeneous space. So this is in homogeneous space and the orbit which sits in your manifold. Again, here maybe it's a good idea to check. So the map is well defined. And it's an isomorphism. So this is just, of course, you may have seen it in other topics, maybe for discrete groups. Right, at the moment it looks pretty abstract. Later on in the course, we're going to use this kind of geometry, maybe already next time. So that's why I thought it's a good idea to mention it already here. And maybe one more thing. So there is a set inside M. There is a subset MG. So these are points of M which are not moved by the group action. So this is a fixed point set. And sometimes it will be, in many considerations, it will be an important object for us. Perhaps just to say that if you have a fixed point, if you have a point M in MG, so then the corresponding GM, the stabilizer group, is simply equal to G. That's more or less by definition, right? So this will be fixed point sets for the group. For some of its subgroups, it will play a big role in symplectic geometry of group actions. Okay, so that's so much about the terminology. Now let me, for some time, and actually our main examples today, we're not going to look at very complicated actions today. We're going to look at very simple actions. And again, probably you know already from other courses much about it. And I will be looking, my main examples today will be linear actions of groups on vector spaces. So we say that M is V, a vector space, is a rule over R, so a real vector space. So in this case, one can be a bit more specific of how linear actions look like. So in particular, let's say rho will be a map from the group to endomorphisms of the space V to linear maps from V to itself. We say that A of GV, so this action, so right, we said that this is the same as G acting on V, will be equal to a linear operator rho of G acting on the vector V. Of course, we need a condition which would ensure that this is indeed an action. And the condition is, so rho of G times H is rho of G times rho of H, right? So in this case, we are saying that rho defines or is a representation of G on V. Right. Again, just to remind you, actually, this equation, it implies several other important facts that we're going to use. So first of all, it implies that rho, the value of rho at the group unit is the unit matrix, and rho of the inverse is the inverse of rho of G. So this is simply consequences of this equation. All right. So now let's go into examples, and I will be looking at very elementary examples today. And my first example, and maybe actually the most important example that we're going to use a lot, is simply when G is equal to S1. So, I will first consider several simple representations. So one representation S1 simply acts on R, and for all angles theta, rho of theta is simply equal to 1. So, so this is a trivial representation. That's, of course, comes for free. Now, I'll describe a one parameter family of representations of S1 acting on R2, so two-dimensional representations. Here, it will be sort of convenient for writing formulas to identify R2 with C. So I'm still consider it as a representation of R, but it might be convenient to use complex coordinates. And then I'm saying that rho n of theta maps Z to exponential I n theta Z, where n is an integer which is not equal to 0. And of course, if I'm using complex coordinates, Z bar will be mapped to e to the power minus I n theta Z bar. So you can actually write it as a linear transformation of R2. So this is equivalent to saying that that there is rho n of theta is the following linear transformation of R2. I hope I got my signs correctly. So I always get wrong signs. So I don't know. I hope here the sign is minus and here the sign is plus. But who knows? Perhaps you can also check. So this is a family of two-dimensional representations. But now, just know that there is one small thing, and I will write it in a kind of, my notation is slightly funny, but I hope it will be clear what this means. In fact, if you change the sign of n, so those two representations which correspond to n and minus n, they're actually isomorphic to each other. And the isomorphism, you can achieve it, well, you can understand it in two ways. So if you exchange the roles of Z and Z bar, right, then it just on the nose that the formulas for this plus n go to the formulas with minus n, and after all, nobody told us how to choose Z and Z bar, so I can do what I want. The other way, if I want to do it in real coordinates, right, that's the same exchange of Z and Z bar. It's the same as the symmetry with respect to the x-axis. So y changes sign, and then this matrix rho n, it will go to the matrix rho minus n of theta. If I just change the sign of the y coordinate. So in fact, for now we have a family of representations with n, for instance, you can say bigger than 0, and we have a trivial representation. So that's these are my examples for now. And then there is the following fact. There is the following fact. So if I take any finite dimensional representation, so V a vector space over R, let's say dimension of V is finite, and rho from S1 to endomorphisms of phi, a rep. So then this representation is isomorphic. Again, I will write it in the following way. So maybe I write it in terms of V. So it is isomorphic to a direct sum of some copies. I don't know how many copies of two-dimensional subspaces. And here I write the index Ni plus V prime. And here those R2 and I, so these are two-dimensional representations that we described before. Let's say this and I in Z positive, let's say to count only once representations with n and minus n. Right, and V prime, sorry, and V prime is a trivial representation, but now of arbitrary dimensions. So a direct sum of trivial representations, as many as we want. And of course, the dimension of V is equal to 2 times m. So the sum of dimensions of those R2s plus the dimension of this trivial component V prime. So the representations of S1 is simply direct sums of those representations that I've just described plus the trivial one. So maybe now a test question, maybe you can tell me in the chat. This is something which is very standard for you. You see it for the first time. How is it? Is it surprising? Is it not surprising? Please react in the chat. Trivial, so it's everybody knows it. Okay, good, perfect. So then consider it just as a reminder. Yeah, good. So maybe later on I'll kind of, in any event, I don't plan to prove it and we're going to use it. So I wanted to show it to you again. And so later on I'll give you a hint. But for now, okay, good. So this is just all standard. So then maybe one more thing, which is also probably quite standard. Suppose we want to lift this story to the product of several copies of the circle. So a real torus, S1 cross S1 and so on. Right. Okay. So here are the angles, theta 1, theta k. And again, of course, there is a, so tk TK can act on R. So trivial representation, right? Trivial action. Let me denote it like this. So this is theta underscore rho of theta equal 1. And again, there will be non-trivial representations. So they are still two-dimensional. X on R2. And now rho of theta, it carries an index n. So that's again a set of integers, n1 and k. And this maps, let me write it again in complex coordinates. So e to the power I, sum over j, and j, theta j, z. So this is just several copies of what we were doing before. Again, rho of minus n is isomorphic to rho of n. And again, for any rep v, we have a decomposition as we had before. Plus the trivial component. By the way, notice that in terms of our previous notation, the prime is exactly VG, so the set of fixed points. Right. I want to show you two more examples, which are, of course, also very easy. So let's say G is equal to UN. And then, of course, just by definition, right, these are matrices. So UN acts on Cn, which is isomorphic to R to the power 2n. But now maybe also something standard, but a little bit more interesting. Let's say n is equal to 2. So then we have U2, and here there is a matrix A, B, C, D. And well, it acts on C2, of course, by linear transformations. Right. And now there is an interesting observation. It goes in any dimension, but in particular for U2. So U2, in this way, we can induce an action on the space of polynomials into variables. So up there, we were moving points of C2, but now we want to act on polynomials by substitution, right? So this is a substitution, and we can act on functions. So these are polynomials into variables, and actually this is a homogeneous action. So we can say that polynomials, they split into a direct sum of polynomials of different degrees. So this is a degree. And of course, U2 acts on each degree separately. So we get a large number of representations of U2 for free. And there will be some simple problem in the next problem set, which is about this action. Incidentally, so here perhaps you should figure out a little bit, if we want U2 to act on polynomials, I think we shouldn't take this formula, but maybe we should take the formula for the linear transformation from the problem set. But please check that what needs to be done for it to be a group action on functions. Right. Finally, a couple of more examples. Suppose that G is a matrix Lie group, and G is its small g, or small beautiful g is its Lie algebra. In general, there is an action of the group on its Lie algebra, but for matrix groups, it's very easy to describe it. It's called the adjoint action, and it goes as follows. So the notation is adjoint G, and it maps X just to its matrix conjugate. So I'm profiting here from my assumption that I'm always working with matrices. Otherwise, I need to describe it in some abstract way. But now I'm just saying that this adjoint action is simply the action by conjugation. So maybe one small remark. So recall that Tn is a group of diagonal matrices, and also the corresponding Lie algebra is the Lie algebra of diagonal matrices. So then for Tn, the adjoint action is simply trivial. So adjoint G is equal to 1 for all G. Oh, sorry. I'm repeating myself. So, you know, we now have a complete classification of representations of T, and for the adjoint representation, we only have a trivial component. There is nothing else. Okay. Now, that, I don't know, perhaps it's a bit surprising, but we need one more representation of G, and it goes under the name of the coadjoint representation. For now, it's not obvious, but it is of key importance for the rest of the course. Maybe this is one of the big points. So we'll see it maybe already next time, why it plays a role. But now, what's the definition, right? So it's a definition, it's a representation in endomorphisms of the dual space to the Lie algebra. So the notation is adjoint star, and it is defined as follows. So, of course, we have a natural pairing between G and G star by definition, and we define this representation as follows. So that's the formula. So we know what is adjoint G minus 1, and this uniquely defines a linear operator adjoint star G. So notice there are two interesting things. Here it is G, and here it is G minus 1. And just a simple exercise, check that this is indeed needed for to have an action. So this replacing G by G minus 1, that's because we want it to be a G action. So perhaps for some of you it's obvious, but maybe for the others it's not so obvious. But I think if you don't know why you have this G minus 1, just check that the operators adjoint star G do define an action, which means that they satisfy the defining property of representations. All right, so this coadjoint representation, now it's prepared in our course. We know what it is, and it will play a big role later on. Maybe already now I want to mention just this simple example. Again, let's say that G is equal to UN, right? So now recall that for the case of UN, we have a particularly nice picture for G star. It is identified with the space of n by n Hermitian matrices. And the duality between the Lie algebra and its dual, it's realized by this imaginary part of the trace. So here we can simply compute this operator, adjoint star G. So this is concretely, in terms of matrices, the imaginary part of the trace of this gadget, whatever it is, times X. And by definition, this is imaginary part of the trace Xi times adjoint G minus 1 of X. But this guy, we know what it is, right? The adjoint action is simply the action by conjugation. So this is G minus 1 xg. Now, under the trace, we can change the order. And this is imaginary part of the trace. And here, G psi G minus 1 times X. Okay, that sounds good. So now we can simply identify things, right? So this pairing, that's imaginary part of the trace. And this means that this mysterious adjoint star G of Xi, this is simply the conjugate of Xi by G. So you see this adjoint action is conjugation, coadjoint action is conjugation. So actually, this is some kind of linear algebra in this particular case. So now maybe one more remark. So suppose we have some Hermitian matrices Xi in Hn, right? So this is isomorphic to G star. And we would like to look at the orbit of this matrix under the coadjoint action. So this goes under the name of a coadjoint orbit. Now, what is this coadjoint orbit in this case, right? These are all conjugates of Xi by unitary matrices. And now I think from the linear algebra, from the spectral theorem, we know the characterization of this set, right? Now it was all very abstract, but now we can say it is something very concrete. So these are actually elements Xi, or maybe let me choose another Greek letter, eta, in Hn, such that eigenvalues of eta are equal to some ordered set. And this ordered set, these are simply eigenvalues of Xi, right? So linear algebra tells us the conjugation by Hermitian matrices, by unitary matrices, doesn't change eigenvalues. And actually, the set of eigenvalues, that's the only invariant. Is the relations with homogeneous space of this coadjoint orbit. Okay, sounds is a good question. Let me say some words about it. So whenever we think of an action of a group on a manifold, we always have two viewpoints. Now I'm talking to you about the following viewpoint. So my manifold on which I act is just a vector space, right? The space of Hermitian matrices, it's a vector space. And on that vector space, I have an action of UN described by conjugation. And what I'm doing now, I'm choosing some point. So that was my point psi. And now I'm describing to you how the orbit of psi looks inside this ambient space. In this case, it's just a vector space. In general, it would be a manifold. And then in that manifold, I'm looking at what happens with a point if I move it by group elements. So that's a kind of extrinsic viewpoint, because I'm thinking of an action on the whole space, and then within this whole space, I'm looking at the subset that I obtain by moving a given point. So this is O psi. But on the other hand, I can also look at it intrinsically. And intrinsically, it should be isomorphic to G mod G psi, right? Where G psi is the stabilizer. Of course, that goes for any orbit, coadjoint or not coadjoint. So in fact, we'll go back to this intrinsic extrinsic viewpoint for coadjoint orbits in quite some detail. But in the meantime, I invite you to think. We'll need to answer that question sooner or later anyways, but I invite you to think, what are the coadjoint stabilizers for this particular example? So what's the set of subgroups? So question. What are those coadjoint stabilizers in this example? To simplify your life, you may think of psi's as only being diagonal Hermitian matrices. So that's enough. Otherwise, there is a more complicated story, because then you will have stabilizers which are conjugate to each other, but not the same. But let's only think of diagonal psi's. That's enough. Right. I'm not sure whether I answered your question. Probably not quite. Right. But of course, all orbits are homogeneous spaces. Coadjoint orbits are homogeneous spaces for some particular subgroups G psi, and we'll need to know what those subgroups are and their properties. And in the meantime, try to make a classification. So classify them. Okay, good. So much for that. So I spoke quite a lot about linear actions. Let me, for a short while, dive a little bit into the theory of general actions. And here there is a topic that I want to touch upon. It's called fundamental vector fields. Again, I don't quite know, maybe you know all that. I apologize if I repeat things. So G acts on M is a manifold, G is a Lie group. Let me assume that G is connected. Perhaps sometimes we'll consider disconnected groups, but mainly our examples are connected groups. And G is a Lie algebra of G. So then let me choose an element in the Lie algebra, and we define a vector field. So let me call it XM. So this is a vector field on my manifold. And it's defined by its action on smooth functions. Right, so vector field should be able to differentiate a smooth function. It's like a first order differential operator. And I'm telling you what's the result of applying xm to a function computed at some point m. So, and here that's the following formula. And I must say, when preparing, so I always get confused about one thing. I'll tell you which one. So you use the exponential map to build a family of group elements which depend on a parameter, on a real parameter. You move your point. So here I'm following the orbit, right? So I have a manifold. In a manifold, I have a point M. And here is the orbit traced by the subgroup. So here, exponential of minus tx m. So I'm taking the orbit of this one parameter subgroup, and I'm differentiating near m, at the point m, with respect to this action. Basically, this vector field, this corresponds to a vector which is tangent to this orbit, and its length depends on how fast my group element is moving the point. So that's the idea. Now, I'm always getting confused by the sign. And I hope I got my sign correctly. It's a little bit counterintuitive. Why all of a sudden a minus sign? It seems to be correct. And there will be an exercise in the next problem set where you need to verify that indeed it has good properties. So here is a small proposition about those vector fields. So suppose that G is a compactly group, and suppose that, and then the following is true. So then, and sorry, I'm connected. Connected was always the assumption. So then, M is a fixed point if and only if xm vanishes at M for all x in G. Okay, why is it true? So this is one of those one-line proofs that I like so much. So in one direction, suppose that M is a fixed point. So then, of course, exponential minus tx acting on M is always equal to M, right? The group doesn't move M. But then the formula with the derivative shows that the derivative is always zero. So if the derivative of any function is zero, your differential operator must be zero, right? So the derivative is always zero. All right. In the other direction is also kind of easier, but maybe I don't write the proof in a very formal way. So in the other direction, we are saying that the vector field vanishes at that point, right? So now we can let's consider Let's consider m of t equal to exponential minus tx acting on m, right? Let's consider the trajectory of our point under this one parameter subgroup. And let's take a derivative with respect to t of that point. That's here that I think I'm cheating a little bit on differential geometry, right? Here I would need to do something a little bit more sophisticated, but let's think of it in a chart. So in a chart, this basically means that, right, in a chart, m is just a set of coordinates. So I'm taking the derivative with respect to this parameter t. Now let me do the following. So that's the same as d over ds exponential minus t minus sx, right? Acting on exponential minus t x acting on m. Here I'm just making the definition of the derivative more explicit, and I'm using the fact that exponential of minus s plus t x is equal to exponential minus sx exponential minus tx. And I put s equals 0, right? But this is equal to xm acting on the point m of t, right? So actually m of t satisfies the differential equation. So dm over dt x is equal to xm of m. But then what happens, right? We have the initial condition m of 0 equal to m, and xm of m is 0. So then, by uniqueness of solutions for nice ODEs, solutions but nice ODEs, our solution is simply, our solution is m of t is equal to m for all t. Now, so I've shown that everything which is in the image of the exponential map doesn't move m. Now, for G compact, exponential map is surjective. And we are done. But in fact, I didn't explain you much, and maybe you know it, maybe you don't, about the geometry of groups. In fact, the argument would also work without compactness assumption. This is just because I wanted to complete the proof with something that we know. But in principle, if G is connected, then you can still find a walk around, and you will see that these two sets, the set of so the set of fixed points and the common set of zeros of fundamental vector fields, they're just the same. And actually, we'll see later on that geometrically, that's a very interesting thing. We'll need the set of zeros of certain fundamental vector fields. So that's what we'll need in our theory. And a priori, if you think of arbitrary vector fields, the zero sets are very wild. They don't need to be submanifolds. They can be very complicated and unpleasant. But we'll see next time that the fixed point sets of actions of compact groups, they are nice. So these are submanifolds and so on. So we're going to exploit this relation. So it sounds like easy-ish, but on the other hand, geometrically, it is significant. So for us, it will be one of the important facts that you can play either one way or the other. Okay. So now let me, for some time, fall back to linear actions.
Can we go back to fundamental vector fields, please?
Sure.
Yes. Is it possible to interpret this as some sort of push forward of x to m?
Sure. Right. Yes. Maybe let me comment. Yes. Of course. So what happens, right? We have an action map. And we can take right. We take, say, a right invariant vector field on G, and we push it to M. So let's say here we have a right invariant vector field XR, right? XR plus 0, nothing on M. And so this is the action map, and we push it forward to M. Of course, we need to check, right? You probably, since you're saying push forward for vector fields, we need to check that actually the vector field projects. So that we need to check, right? This is a map which kills many things. So we need to see that if we come from different points on G cross M to the same point of M, we get the same image. Right? This is an easy exercise, and yes, indeed. So you can simply think of XM as a push forward of the right invariant vector field. Remember, we introduced those vector fields parameterized by the elements of the Lie algebra. You can push it forward. You obtain the fundamental vector field on M. Right. So I don't know whether it's a very good picture for everybody. Of course, it's much shorter than what I just told you before. Is it satisfactory? Is it a good answer to your question?
Yes, thank you.
Mm-hmm. Okay, perfect. All right. So I want to dive back to the linear actions. So suppose we, sorry, maybe let me state, well, yeah, I forgot an important thing. So let me state a theorem, and this theorem is actually an exercise in the next problem set. So this theorem says the following. So suppose we take any two elements of our Lie algebra. So then we can construct the corresponding fundamental vector fields, and we can take its what is called Lie bracket, or it's actually just a commutator of operators on C infinity M, right? Or you may know, right, the construction of a Lie bracket of vector fields. And this will be equal to the Lie bracket. For us, for matrix Lie algebras, that's just a matrix commutator. And then computed on M. So here, I think you need this minus sign somewhere. And I think, by the way, this probably means that here it is minus XR that I need to take, I guess. So, right. From this picture in the comment, this should be more or less obvious. You can choose any method in your exercises to prove it. And that's, of course, a very important fact. So here we are saying that the commutator of fundamental vector fields is the same as the Lie bracket of elements of the Lie algebra. All right. So back to linear actions. So again, we look at linear actions. So here the context, let me remind you, we're looking at a representation in some finite dimensional vector space. And let's choose an element of the Lie algebra. And then by abuse of notation, we define rho of x. And rho of x is defined in a way which is a bit similar to what we were doing before, but now with a plus sign. Right. So we're taking an operator of our representation and we take a derivative at t equal to 0. So, of course, here maybe I could have changed the notation and not to reuse the letter rho twice, but I think traditionally you denote it in the same way, by the same pattern. And here is a theorem about this construction. So first of all, so this rho from G to endomorphism of V that we've just defined is a linear map, which I still find, whatever, after that many years, I still find a little bit surprising. And the second statement is that similar to the theorem that we stated before. So the commutator of rho of x, rho of y is the same as rho of xy. So in fact, these two statements with the axioms of a representation of a Lie algebra G. So, you know, this is actually a piece or whatever, one of the entry points of the big theory. So we have groups, Lie groups, and we have corresponding Lie algebras. And we can ask, what's the relation between representation theory of in these two categories? So we have representations of groups, which were defined in the beginning of the class, and you probably know anyways what they are, right? Defined by linear operators which satisfy this equation in pink. And now we have representations of Lie algebras, which are defined by this set of conditions. And you may wonder whether one can go between these two notions. So in simple cases, like our case for compact groups, there is simply a one-to-one correspondence, and the differentiation, usually it's referred to as differentiation because you see it defined with the derivative. When you go from a representation of a group to representation of a Lie algebra, it's just this formula. And in a second, we'll see how you go in the opposite direction. In general, that's a complicated story, and usually there is not one-to-one correspondence. Sometimes you can go one way, sometimes you can go the other way. So it's a big theory which continues to develop. There are many classical results in it, but for us, of course, it's all going to be very simple. But just to tell you that here we're sort of lucky. I presented as a part of background material, which is easy-ish, but the general framework is interesting, and even though it looks elementary, the answers are complicated in general. All right, so let me try to show you some elements of the proof. So first of all, even though it sounds obvious, or I don't know whether, to me it doesn't sound obvious that this is a linear map. So let's prove that this is actually a linear map. And let me prove separately that you can multiply by scalars and that you can add things. So for instance, if I multiply by scalar, right? So this is what? This is d over dt rho exponential of tax, right, at t equals 0. Well, here, of course, what I can do, I can say that now my new variable is t times a. And this would mean that here, let me simply make a change of variables, right? T times a is my new variable, and here I need to multiply by a. So now this simply implies that this is a times rho of x. So this property is sort of obvious. Now, here is what happens with rho of x plus y, and I don't quite know. I must say I'm still a little bit confused where I presenting you an optimal proof. So maybe some of you may have thoughts about it. That would be very welcome. Right, so I need to compute this and convince myself that this is a sum of rho of x plus rho of y. Okay, why is it true? So I came up with the following. So first of all, I note that if I add here in the exponential anything which is O of t squared, right? Just anything. This cannot possibly change the result, right? Okay. Now, in the previous problem set, you saw this Baker-Campbell-Hausdorff formula, and this formula is telling me that I can add such a tail, this O of t squared, such that here I would get exponential of tx times exponential of ty, right? So this product is of the form that I want, right? And now this is, I can use the representation property. This is rho exponential tx, rho exponential of ty, and at t equals 0. Well, but now I can simply use the chain rule, right? So this is rho of x, right, times t equals 0 value of the other guy, which is 1 plus 1 times rho of y. And that's what I wanted. So here is a small challenge. I'm not sure. I'm kind of, is it really the easiest proof one can come up with? Yeah, I'm not so sure. Maybe kind of maybe your comments would be, so this is certainly proof, yes, but, at least how I present it now, it sounds like it's a non-trivial property, right? I'm using the Campbell-Hausdorff series, I'm using the representation property, and I'm using everything, more or less. Okay, now what about—
May I give a comment?
Sure. Yes, please.
Well, we could sort of cheat in a way and give a different definition. So we have just a map of smooth manifolds from G to GL of V, and then we take a differential at unit.
Okay, okay, sure. Yeah. Of course. Then, of course, the linearity will be obvious. Yeah, I agree. No, sure, that would be, I don't know even if it's a cheat. It's a little bit of a cheat because you know, I'm giving you a very concrete formula which doesn't bug you with any differential geometry. So it may be, of course, one may have a suspicion then if I wanted to show that my definition, which is very, very concrete, and your definition, which is very clear conceptually, but somewhat abstract, that they are the same, maybe there I would again confront the same question. Of course, the map that you're suggesting is clearly correct. So there is a question on the chart asking whether it is a Taylor series. Oh, sure. The definition here, the differentiation. Yes, of course. So we know that that row or the group row. So maybe here I can. So so row of exponential of tx, right? We know that at t equals 0, it's 1. So here we know, and then now what the formula is saying, it is t row of x plus O of t squared. So yes, it is just the first term of the Taylor series. That's right. With respect to t. But I mean, why should it be linear with respect to x? This is right. The linearity of first order of Taylor series is obvious. For t, yes, sure. But for x, how do you know that? You see? But okay, maybe one can. Well, of course, it also goes in the same direction that this is a derivative. So this is a differential of the action map. So that one is clearly linear. Okay. No. I mean, it's good. We're discussing. Well, why are you sorry? I'm grateful for your comments. All right. So let me jump to the last to this equation. Row of x, row of y is row of xy. So here again, I built some kind of proof where I again suggest you to see whether it's an optimal one, maybe not. So I'm looking at a two-parameter family: a row exponential tx, exponential sy, exponential minus tx. So this is equal to, of course, the by representation property, right? It's equal to this. And this is equal to row exponential t. Sorry. So here I'm using that I'm a matrix guy, right? Exponential s tx y minus tx. So that's because I'm in a matrix group. Otherwise, I need to do more. Okay, so this is my starting point. Right, so I consider this two-parameter family, and all three expressions, they are clearly equal to each other. Right? Now, I'm doing the following. I'm doing d over ds at s equals 0 on all the sides. More concretely on these two expressions. I'm not interested in the expression in the middle, but I'm doing this. Okay. So on this side, it gives me a row of etx y e minus ty. And here it gives me row etx, row of y, row e minus tx. Right? And here I'm just using definitions. Now I'm doing, sorry. Now I'm doing d over dt at t equals 0. D over dt at t equals 0. And on the left, you know, since this is a linear map, I can simply differentiate under the sign of rho, right? Rho is a linear map, so I can differentiate over t the argument, and that's that will be it. So this will be rho, and here it will be xy minus yx, right? That's the derivative of over t at t equals 0 of that thing. And on the right hand side, I'm just using the definition and the Leibniz rule. So it is rho of x, rho of y. Yeah. And they are equal to each other. So I don't know whether it needs to be that complicated, maybe not, or maybe yes. And here I'm using the linearity. Linearity of rho is crucial. Otherwise, if rho is a nonlinear map, of course, this arrow simply doesn't hold. Okay, perfect. So now let me give you one example, and then I want to formulate a theorem that we're going to prove next time. But I need that theorem for your problem set. I was thinking that I would have time to prove it, but maybe it's only to the better. We postpone the whole thing to next time. So we do the example, and I just finish with the theorem. So an example, you can imagine what I take. So I introduced those representations of S1. So they are parameterized by positive integers. Right. So theta, I consider it as an element of S1, which is the same as R mod 2 pi Z. And the Lie algebra of S1. Well, now I don't quite know. According to what we were doing up to now, we would say that it is imaginary axis. Of course, it's also isomorphic to the real axis. People do both things. Let me maybe stick to this notation, even though naturally, if I were not given a course, probably I would have thought for myself that Lie algebra of S1 is R, but to be consistent. So we'll now be computing, let me call it D. So this will be the image dn of the imaginary unit. And by definition, this will be d over d theta rho n of theta computed at theta equals 0. So now theta is my parameter t that I used before. Right? and x is just equal to 1. So, of course, that's a very easy computation. It gives 0, minus n, and 0. So this is an example of a representation now for a Lie algebra. And if here I introduce ix, then there would be an x. So this is our representation of the Lie algebra of S1 acting on our two-dimensional representation with index n. All right. So now this theorem. I had several motivations to introduce this theorem. One, it's going to be important for us. It will be useful for the next problem set. And also, last time someone complained that we dived into those groups and group actions, and we don't do anything symplectic. So 4 minutes to do something symplectic today. And of course, it will develop next time. So suppose that the omega be a symplectic vector space. And so that's for the first time we are combining things, right? So let's say S1. Be a representation such that there is an extra property. We want omega to be invariant under the S1 action. So what does it mean? That means if you move your vectors by the group action, the symplectic form doesn't change. Right? So this means is invariant under the S1 action. And this will be the context for many statements later on. So we're going to look in general on manifold symplectic structures which are invariant under S1 actions and actions of other groups, usually compact Lie groups. All right, so then what? Now, V viewed as a symplectic vector space with an S1 action is isomorphic, and the right-hand side you could also already guess, right? You have a sum from 1 to m, and here there will be again the actions of S1 on R2. Remember, we had this classification of representations, which was clear to you. And on R2, as a vector space, there is not a big choice of symplectic structures. So there is essentially only one. So we can equip R2 with that symplectic structure, and then we add V prime, which is a trivial representation with some symplectic structure, omega prime. So this is a trivial S1 rep. So this is actually kind of interesting result. It basically tells you that, right, we had on the one hand, we know that in given dimension, the symplectic structure already in linear algebra, it doesn't have any invariance. They're all the same. Okay. Now we know that representations, well, for S1 or for the torus, so there is some kind of classification. It's an easy classification, but well, okay, there are those direct sums of R2s plus a trivial component. And now it turns out that one can make the symplectic form a slave to the action, right? So the symplectic form obediently also splits into the direct sum of symplectic forms for each component where you have an R2 action, right? So basically, the group action decides for you. Up to now, the symplectic form follows. It doesn't object. All right, so that's a good point to stop for today. Next week, we're going to start from here, and we're going to talk more about invariant symplectic structures on manifolds. So we're going to considerably advance that theory next time. All right, thanks a lot. I don't know whether you have questions. Yeah, please go ahead. Simeon? Yeah. Is the quiver representation has the relation now let's say maybe I have a somewhat roundabout question. Of course, these are both okay. One thing that these are both instances of representation theory, right? Of course, representations of a quiver a priori have a rather different nature from representations of a given group, especially such simple examples as we were looking at today. Still, these are, we can say, representations. We have some kind of algebraic, or let's say maybe, yeah. So we have some kind of algebraic structure, and with given operations, right? Because in a quiver, we would say these are, I didn't formulate it that way, but one should consider pods. One should consider pods in a quiver. You can see, you can in principle force them to be an algebra. So you have some kind of algebra, and so it's a representation. It will be a representation of that path algebra. And for a group, you can also think, let's say, to make it comparable, you can try to consider a group algebra, group ring. So one can make those things sound close to each other, but right. Okay, so the next question is, when we go to the localization and ATIA moment map. So localization, let me see. So probably before, let's say, before localization, we should do reduction. Maybe we start it next time, or maybe just after the midterm test. That we need to, we will see. Maybe next time will be still examples, and then okay, reduction. Then I'll need to decide. There, remember, there are three big theorems we need to do: reduction, convexity, and localization. So I will have to decide whether convexity goes before localization or the other way around. So that's still to discuss. But okay, sometime during the second half of the course, that's one of the big theorems that we need to look at in detail. So a TM moment map theorem, that I don't know what it is. Do you mean convexity? Yeah, right. So as I say, these are basically for after the midterm, we have three big things, maybe already to start next time, but we have three big things to do. Reduction, and reduction is an easy theorem, but many examples. Convexity is more like a difficult theorem, and localization is, I would say, it's probably more like an easy theorem, but it's related. Localization is related to the moment map. So, okay, you suggest to speed up a little bit. Okay, if that's a general opinion, sure. But I mean, I'm quite sure those statements, they all fit in. So no worries about that. Of course, we can speed up, but everybody shares this opinion. That's sure, no problem. Just maybe express your opinion.
We can try to check this with the Telegram group to see if there is.
Yeah, right. Maybe.
Sure, but I think it's. I could guess that it's probably true. Yeah.
Okay, yeah, sure. I would be happy to. Of course, we still, we need to speed up, but still understand what's going on, right?
I'll ask everybody to vote on Telegram, at least so that it's.
That's a very good idea, and then you let me know. I would be very happy to kind of to do some more advanced stuff. Sure. All right. More questions, people? Okay, good. Then maybe also if you vote on speeding up, because now you know what you need. Kind of basically we are doing like we're using groups, we're using differential geometry. Also maybe tell me whether any of this stuff presents some difficulty for you. Differential geometry, or if of course if everything is smooth, we can go faster, maybe even considerably faster.
Well, this is the downside of distance communication. If you were in a room with them, you would understand in 5 minutes from their faces, but you don't see them.
Okay, but in any event, any kind of feedback will be very useful. Okay, so thanks a lot. If there are no further questions, yeah, okay, so then see you in a week from now. Bye-bye, everybody. So should I leave you the session open? Ian?
Well, I mean, if I'll tell you what, if people want to, I noticed it's actually true that you can stop the recording actually.
Oh yeah, okay.